Okay, welcome back. This is Module 2. We're going to talk about some radical functions. In this particular video, we're going to talk about how to graph square root functions and inequalities using key features, how to graph general radical functions using some key features, and also how to identify and interpret the key features of the graphs within the real-world context the function represents. Okay, so in general, the graph of y equals the square root of x, remember that is a radical function. This little symbol here, that's called a radical, looks something like this. So when we graph that, we have those points. And so if we're talking about the end behavior of a square root function, x doesn't go to negative infinity. X stops here at 0. So as x goes to 0, y goes to 0, and then we go up the function here, and as x goes to infinity, y also goes to infinity. This puts our domain, our x values, starting at 0. So our domain goes from 0 to infinity, and our range, the y values go up forever, also starts at 0 and goes to infinity. There is no symmetry here. It's not symmetric about the y-axis, and it doesn't have rotational symmetry about the origin. Since y goes up forever, there is no maximum. The minimum, however, is right here, is at 0, 0, which makes the x-intercept 0, 0, and the y-intercept 0, 0. Okay, so as we talk about how to transform these functions, what I want you to do is go ahead and go to desmos.com, or you can use a graphing calculator. And first thing I want you to do is go ahead and predict what you think this graph will look like based on what you know about function transformations. So I'll pause the video right now and do that. Okay, and then I want you to go ahead and predict what you think this graph will look like. Okay, and now I want you to go to, as I said, either Desmos or use your graphing calculator. Go ahead and actually graph these two functions, and I want you to see if your predictions are correct. So pause the video when you're ready to come back. Okay, and now I want you to do the same thing. Go ahead and predict what you think this graph will look like. Predict what you think this graph will look like. Pause the video when you're ready. Okay, and I want you to go ahead and actually graph those, and I want you to see if your predictions are correct. Okay, so in general, when we're transforming square root functions, we're still going to talk about transformations in terms of a, b, h, and k. Remember that a is going to be that vertical stretch when a is greater than 1, and it's a compression when a is between 0 and 1. Remember, when a is less than 1, we're talking about a reflection across the x-axis. B is your horizontal stretch or compression by a factor of 1 over b. And when b is negative, we're going to reflect across the y-axis. H and K is still our vertical translation up and down, and H is our horizontal translation left or right. Okay, so if we're going to graph square root functions, we already know what the basic shape is going to be, and we know that we need to pick x values that are going to cause the numbers under the square root to be positive. So we can go ahead and just pick some x values and make an xy table. We can also look at each square root function as a transformation of the original parent function. So, for example, here we know that the square root of x minus 1 means h here is 1, and k is 3, and a is negative 1. And that means that our parent function has been translated right 1 unit, up 3 units, and reflected across the y-axis or y has been made negative. So when we create our table, rather than just randomly picking x values, we can actually use the fact that the x values are moving right 1. Well, if you move an x value right 1, you're basically adding 1. So when we start at 0, 0 plus 1 is 1. 1 plus 1 is 2. 4 plus 1 is 5. 9 plus 1 is 10. And 16 plus 1 is 17. And so now I can put these x values into my equation. And 1 minus 1 is 0. Negative 0 is 0. Plus 3. So 3. Or I can think of this as what I'm doing to my points. And up 3 means I'm adding 3. Reflection about the y-axis means I'm making the y value negative. So basically, I'm making this y value negative and then adding 3. So basically, I'm doing negative y and then adding 3 additional points. So the negative of 0 is 0, plus 3 is 3, of course. So that's why this is 3. So again, 2 minus 1, square root of 1 is 1, negative 1, plus 3 is 2. Or if I make this 1, negative 1 plus 3, I get 2. Negative 2 plus 3 is 1, and I can confirm that if I put 5 in here, I'll get the same thing. Negative 3 plus 3 is 0, and negative 4 plus 3 is negative 1. And so now I can graph my new function. So 1, 3, 2, 2, 5, 1, and 10, 0. And so when I graph this, it looks like that. And when I talk about the key features, as x goes to 1, because it doesn't go to negative infinity, y goes to 3. As x goes to infinity, y goes to negative infinity, because my values are going down here. My domain is going to be x values from 1 to infinity. And my range has a maximum of 3, so that means my range can go from negative infinity up to 3. There is no symmetry. My maximum is going to occur at 1, 3 here. There is no minimum because my y values are going to go down forever. My x-intercept occurs right here at 10, 0. And I'm never going to cross the y-axis, right? I'm not going to have a y-intercept because I start at 1 and I go right, so there's no y-intercept. Okay, so I want you to go ahead and try this on your own. You can use the exact same steps that we used. So pause the video right now, try it. Okay, welcome back. So if you use transformation of the parent function, remember this was the original parent function. I'll put the XY table up in just a moment, so if you don't want to see that, go ahead and cover, and then we'll move on to the next example. Okay, here are the XY and the key features, so pause the video if you want to check those out. Okay, so the next thing we're going to do is graph a square root inequality, and we can do this by still graphing the equation as normal. So we notice that this is plus 3, so that means we've moved left 3. B is negative, so we are reflecting across the x-axis, and plus 4 means up 4, right? Okay, so I'm going to pick some x values that are going to make this perfect square. So here, or I can again use my basic 0, 0, 1, 1, 4, 2, 9, 3 pattern and translate that. So if I want to force this to be 0, if I pick 3, so if x is 3, then negative 3 plus 3 is 0 plus 4. In order to force this to be 1, if I pick this as 2, negative 2 plus 3 is 1, and plus 4 is 5. If I want to force this to be 4, then if I pick negative 1, the negative of negative 1 is 1, plus 3 is 4. Sorry, the square root of 4 is 2, and so you get 6. Sorry, excuse me, negative 1, 6. In order to force this to be 9, I'm going to go ahead and pick negative 6. So the negative of negative 6 is positive 6, plus 3 is 9, square root is 3, plus 4 is 7. And remember, this was a 6. And I could, if I force this to be 16, this would be what's in here to be 16. This would have to be negative 13, which puts me off my graph. But negative 13 plus 3 is 16, the negative of negative 13. 4 plus 4 is 8. Okay, so this is a strict inequality, right? Y is strictly less than this equation, so that means I'm going to do a dotted line. So I go to 3, 4, so 3, 4 is here, and then 2, 5, and then negative 1, 6, and then negative 6, 7, and then I'm off my graph. But now I'm not going to draw a steady line because this is a strict inequality, which means I'm never actually going to equal this function. I'm going to get super, super close, but my solutions never actually equal that function. It never actually equals that line. And the y values are less, so I'm going to pick a point underneath down here. This is my test point. 0, 0 is always the easiest test point. So I'm going to pick 0, 0 and then put that in. So 0 should be less than the square root of negative 0 plus 3 plus 4. So my test point is 0, 0, and I put that in for my xy values. So 0 should be less than the square root of 3 plus 4. The square root of 3 is a little between 1 and 2, but certainly that is greater than 0, so that would check out, which means that this could be a solution. Now, these values here, okay, are also included in the solution. So we're going to shade everything to that side, okay, because we cannot have any y values, or excuse me, x values that are greater than 3, and we can't have any y values that are equal to or above the function that we drew right here, the green function. So when we look, is negative 4, 7 a solution? So if we look for negative 4, 1, 2, 3, 4, 5, 6, 7, we can see that negative 4, 7 is just above the function. So negative 4, 7 is not a solution because it is not in the shaded area. So it's not a solution because it's not in the shaded area. Or you could just test it algebraically. So is 7 less than the square root of the negative of negative 4 plus 3 plus 4? So 4 plus 3 is 7. So is negative 7 less than the square root of 7 plus 4? The square root of 7 is between 2 and 3, so a little bit less than 3. And so, sorry, that's positive 7. So 7 would have to be greater than this because this is less than 3. So this is not going to work. Okay, I want you to go ahead and try solving a square root inequality. Go ahead and pause the video right now. Okay, welcome back. So if you made an XY table, you notice that 10(3) is not a solution to this inequality. Your inequality should have had a solid line because it's greater than or equal to, and it would have been shaded above the function. Okay, so the other type of radical functions that are most often talked about are cube roots. So we often talk about square roots and cube roots. But there are also nth roots, and we'll talk about those later. So a cube root function are all of the points that satisfy y equals the cube root of x. So is the inverse of cubing something. So when we look at this, we notice that our graph is going to go to the left and to the right forever. So as x goes to negative infinity, y goes to negative infinity. And as x goes to positive infinity, y goes to positive infinity. Which means that our domain is going to go from negative infinity to infinity. And our range is also going to go from negative infinity to infinity. This graph is symmetric. You'll notice it is for every xy value, we have a negative xy value. So it is odd symmetry because it does satisfy that f of negative x equals negative f of x. If we put this in, if I put negative x in, the cube root of negative x is negative cube root of x. There is no maximum because it's going to go up forever. There is no minimum because the graph is going to go down forever. The x-intercept for the parent function is at 0, 0, as well as the y-intercept also at 0, 0. Okay, so when we graph these, just like we graphed the square root function, the easiest way is going to be to talk about the translation of this function from the parent function that I've just graphed for you here. So when we look at this, x plus 1 means we're going to move left 1. Minus 4 means down 4. And a equals 4 means a vertical stretch of a factor of 2. Okay, so when we're looking at our table, that means we're going to take all of our x values and we are going to move left 1. So if we're moving left 1, that really means x minus 1, so we're subtracting 1. So instead of negative 8, we're going to have negative 9. Instead of negative 1, we're going to do negative 2. And so 0 minus 1 is negative 1, and 1 minus 1 is 0, and 8 minus 1 is 7. Okay, so basically we are subtracting 1 from all of our original x values. Then a vertical stretch by a factor of 2 and down 4 means we're going to take our y values and we're going to multiply them by 2, and then we're going to move them down 4, so subtract 4. And so we can apply that transformation to these y values, or you can put the x values in and solve for y. So negative 9 plus 1 is negative 8. The cube root of negative 8 is negative 2. Negative 2 times 2 is negative 4. Minus 4 is negative 8. And we can see that that holds true because negative 2 times 2 is negative 4, minus 4 is negative 8. And so that works both ways. So for negative 1 times 2, we'll get negative 1, minus 4 is negative 5. And you can double check that that fits into this function. So 0 times negative 2 is 0, or excuse me, times 2 is 0, minus 4 is minus 4. 1 times 2 is 2 minus 4, negative 2. And 2 times 2 is 4, minus 4 is 0. And so our new function is going to go negative 9, negative 8, negative 2, negative 5, negative 1, negative 4, 0, negative 2, and 7, 0. And so when we graph this, it looks something like that. And we can confirm, since this is kind of our original center point, we move left 1, down 1, 2, and we vertically stretched it by 2. Okay, I want you to go ahead and try this, so pause the video right now. Welcome back. Okay, if you don't want to see the final XY pairs, go ahead and cover up that box. Okay, so in general, when we're talking about parent functions, so the square root is what we talked about here, so y equals the square root of x. When we're talking about any radical function, we're talking about n in the integer set. Remember, this guy means in the integer set. So we can talk about square roots or cube roots or fourth roots. And so this is a good generalization of any radical function. And we're going to talk more about nth roots a little bit later. Okay, so how can we rewrite a function so we can graph it using transformations? In this case here, we have a b, but we're not sure if we're moving right 18 or if we're going to move 2. So we can rewrite this equation using our radical rules. So if we know that y equals the square root of 9x plus 18, we can go ahead and factor out a 9. And so 9 times x plus 2 is an equivalent form. And of course we can take the square root of 9. Remember, the square root of 9 is 3. So we can rewrite this as y equals 3 times the square root of x plus 2, and rather than talking about it in terms of a horizontal stretch or compression, we can talk about it in terms of a vertical stretch of 3, and then, of course, left 2. So we can say that this is a graph that's moved left, so y equals the square root of x was moved left 2 units, and vertically stretched by a factor of 3. Okay, go ahead and try those, rewrite them so that you could graph it using the transformations, and then go ahead and describe the graph. If you want to pause right now. Okay, if you want to just check part A first, here's the answer for part A. If you want to pause it now and try B now that you've seen the answer for A, I'll give you a moment. Okay, welcome back. Here's the answer for B. So if you want to read those and pause. Up next, we're going to talk about graphing radical functions, or composition and inverse functions. So if you want to go ahead and complete the 4-1 graphing functions reflection right now, if you need some more help, go ahead and watch the more examples video. Otherwise, up next, section 2, 4.2 is composition and inverse functions. Thank you so much for listening.